When you're given a function like we have in number 1, the limit as x approaches 0 of the absolute value of x divided by x. Again, anytime you're asked to find a limit, remember we always try and do direct substitution. So when I plug in 0 for x, notice that gives me the indeterminate form of 0 over 0. Remember, as we saw from last night's homework, that doesn't tell us anything about the limit. The issue becomes, however, with this function, we know we have the algebraic techniques we can try to find the limit. We can factor and cancel. We can simplify complex fractions. Or we can use rationals. The issue is there any algebra here to do in order to recreate this function? There's no algebra to do. So if you don't have any algebra to do, and you get that indeterminate form of 0 over 0, you have to rely on the graphs. So if you get the indeterminate form and there's no algebra to do, that's where you're going to always have to sketch a graph. Now, I have no idea what the graph of absolute value of x divided by x looks like, so this is where I'm just going to create a little t-chart. And let's find some points on this particular graph. Again, what I'm concerning myself with is the behavior as we're getting really close to 0. And again, is this a one-sided or two-sided limit? Two-sided, so I have to look on the left and from the right. So what I'm going to do is pick some x values smaller than 0 and some x values larger than 0 to see what this graph is going to look like. So let me start with an x value larger than 0, so let me start with 1. So when I plug in 1 for x, what is the absolute value of 1 divided by 1? 1. So let's plug in a 2. If I plug in 2, what's the absolute value of 2 divided by 2? 1. If I plug in a 3, what's the absolute value of 3 divided by 3? 1. Are we noticing a pattern? Yes. If I plugged in 1 million for x, what is the absolute value of 1 million divided by 1 million? 1. So if I plugged in, let's say, 0.000001 divided by 0.000001, what's that value going to be? 1. So you agree with me then that as I'm coming from the right, again, as x approaches 0, the y values are all 1. So that's what's happening on the right-hand side of 0 for those x values slightly larger than 0. So now let's take a look and see what's happening to the left of 0. So again, I'm going to pick some x values slightly smaller than 0, so let me start with negative 1. Well, what's the absolute value of negative 1 divided by negative 1? Well, I know the absolute value of negative 1 is what? 1, but then I'm going to divide it by negative 1. So then it's going to be a negative 1. So what happens when I plug in a negative 2? The absolute value of negative 2 is 2 divided by a negative 2, which is a what? Negative 1. Notice the pattern that I'm creating. What happens if I plugged in negative 1 million? Negative 1. So again, notice to the left of 0 then, that's what the graph is going to look like. So like I said, ladies and gentlemen, what happens if you get that indeterminate form of 0 over 0, and if there's no algebra to do, you've got to look at the graph to decide what the limit's going to be. So you may not have any algebra to do for all those 0 over 0 indeterminate forms. So like I noticed from the graph, what happens as we approach 0 from the left? As we're approaching 0 from the left, we're getting close to negative 1. As we're approaching 0 from the right, we're approaching 1. Therefore, the question is, does the limit as x approaches 0 of absolute value of x over x, does this two-sided limit exist then? No. Again, it does not exist because the limit from the left as x approaches 0 from the left of f of x does not equal the limit as x approaches 0 from the right. Remember, for those two-sided limits to exist, what happens on the left has to be the same as what's happening on the right. So any questions on how you handle a limit situation when you end up getting a 0 over 0 using direct substitution and you don't have that algebra to do? Yes?
On the quiz, will there be questions like what we just wrote explaining why the limit doesn't exist?
I mean, you have to know that. If I ask you to justify, yes, you'd have to write that. Yeah. Mm-hmm. Yep. Okay. So now, besides using a graph, You can also look at tables, as you know, just to review what we did on the first day of doing limits. Again, I know that when I plug in 0, that's going to give me 1 over 0. But let's take a look out and fill out this table and see what's happening. So I'll go to my y equals, type in 1 divided by x squared. So now I'll go to my table, clear out all those values. So I plug in negative 0.01. So when I plug in negative 0.01 in for 1 over x squared, I get 10,000. When I plug in negative 0.001. Now remember, when you get this 1e to the 6 on the calculator, that's the scientific notation that the calculator is giving you. That means you have a 1 followed by 6 zeros. So I have 1, 2, 3, 4, 5, 6. So I end up with 1,000,000. And then negative 0.123 zeros and a 1. I end up with a 1 and then 8 zeros. So 100 million. So now if I look slightly larger than 0, so I go to the right of 0 and let me plug in 0.0001, again I end up with 100 million again. If I plug in 0.001, I end up with that 1 million. And if I plug in 0.01, I end up with 10,000 again. What is happening with the behavior of these y values? As I'm getting these values closer and closer to 0 without being equal to 0, am I approaching a fixed y value? No. What's happening? They're getting larger and larger. So what am I approaching? I'm approaching what? Infinity. So we just got done, ladies and gentlemen, back in Unit 8, graphing 1 over x squared. Graphically, what is happening at x equals 0? Remember we talked about vertical, horizontal asymptotes? What's happening at x equals 0 at this particular graph? We have a what? What do we have at x equals 0? We have a vertical asymptote. So remember, as your graph approaches a vertical asymptote, as you can see, remember, as your graphs are approaching a vertical asymptote in this case, remember the behavior of the function is going to go up towards positive infinity or down towards negative infinity. All right? So when we have a limit as it's approaching a vertical asymptote, we do not say D and E. A better answer is saying infinity or negative infinity. You're talking about the behavior of the function when we talk about a limit. So technically, I agree with you, infinity is not a number. Technically, the limit does not exist. But if you are approaching an asymptote, and that's why you still need to remember how you find those vertical asymptotes, you want to make sure that if it's a vertical asymptote you're approaching, your answer is going to be infinity or negative infinity. It's a better justification for the limit. All right? So now you guys go ahead and do number 3. Fill out that table for me again. When you're dealing with trig, guys, just a reminder on your calculator, you need to make sure your calculators are in radian mode. Anytime you're dealing with trig on the calculators, make sure you are in radian mode. So go ahead and fill that table out for me. All right, so we should, ladies and gentlemen, have gotten these values in the table. I'm sorry, I don't know why I wrote it underneath and not in the boxes. So 0.862, 0.562, negative 0.95, and on the other side. So, ladies and gentlemen, if you look as we're getting closer and closer to 0 from the left and from the right, it appears that we're getting really close to negative 1, doesn't it, in terms of that limit? It looks like we're getting really close to negative 1. If you look at the graph, this is what that graph of cosine of 1 over x looks like. And again, I know that if I do a direct substitution and plug in 0 for x, 1 over 0 is undefined. So again, I know that I'm going to have a hole down here. It looks something like this. So if I sketch this graph, guys, if I sketch this graph, this is what it's going to look like. So as I'm getting closer, and you can see this on the calculator, as I'm getting closer and closer to 0 from both the left and from the right, notice I'm approaching that y value of -1. So like I said, guys, if you get direct substitution and there's no algebra to be done, you've got to go back and follow on the graphs or filling out your tables in order to figure out whether or not this limit's going to exist or not. All right, so any questions on that? All right? Shh, guys, shh. So now, we've been talking about limits, and just a reminder, the conditions in which a limit is not going to exist. So remember, when we're finding limits, again, if f of x approaches a different number from the left side of C than the value approached from the right side of C. Remember, the limit as x approaches C, if it's a two-sided limit, what's happening on the left has to be equal to the limit that's happening on the right. If it's not, that two-sided limit does not exist. Another condition where a limit's not going to exist is if f of x becomes infinitely large. And we would say that that would be infinity. Or small. Which we would say negative infinity as x approaches C from either side. And again, this happens when you're approaching a vertical asymptote. So if you're finding the limit of a number that's actually a vertical asymptote in the graph, that's when you're going to have that infinity or negative infinity as the limit. Again, oscillation, which we'll take a look at not in this section but later on. An oscillation is when your graph kind of bounces back and forth between two different numbers. It bounces back and forth. We call that an oscillation. We actually did, ladies and gentlemen, this is actually going to be a review of what we did back in Unit 8. We've actually already done limits at infinity. Remember, when we talk about the behavior of a function when x gets closer to a particular value C is known as the function's limit. And remember, we talked about in Unit 8 horizontal asymptotes. When we talked about the end behavior, if you remember back from Unit 8, the limit as x went to positive infinity or negative infinity was referring to the end behavior. One of three things could happen. If it goes up, we say that the limit as x goes to infinity is infinity. Or if it points down, we would say the limit as x goes to infinity is negative infinity. Or if you have a horizontal asymptote, it's going to be the value of the horizontal asymptote. So again, like I mentioned, the limit as x approaches positive or negative infinity is going to correspond to the horizontal asymptote. Just a review of the rules that we went over back in Unit 8. Remember, you look at the highest degree of the numerator and the highest degree of the denominator to find the horizontal asymptotes. Remember, one of three things can happen when you're trying to find the horizontal asymptote. The degree of the numerator is equal to the degree of the denominator. If this happens, remember, it's the coefficient of the numerator, the coefficient of the denominator. You look at your leading coefficients. You make that fraction to find your horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, remember your horizontal asymptote is at y equals 0. If the degree of the numerator is larger than the degree of the denominator, the top is bigger. Remember, there is no horizontal asymptote. Then we'd have to look at the end behavior. It would be infinity or negative infinity for the end behavior. So let's take a look at this example right here. The limit as x approaches infinity. So again, anytime you see that x is not approaching a number, it's approaching infinity, this is where you're going to look, and all you need to do is find the horizontal asymptote. So again, the only difference from what we've been doing is now instead of x is approaching a number, it's approaching infinity. This, remember, is the horizontal asymptote or your end behavior. So anytime you see that x approaches positive or negative infinity, you want to find the horizontal asymptote. So let's take a look at 1 over x. We've got to decide which of these three conditions we have. What is the degree of 1? What is the degree of the numerator? To 0. What's the degree of the denominator? 1. So 0 is less than 1. So if the degree of the numerator is less than the degree of the denominator, what is the horizontal asymptote going to be? The horizontal asymptote is going to be at what? 0. So the limit as x approaches infinity of 1 over x is 0. Let's take a look at number 2. Again, the limit as x approaches negative infinity. Again, what you need to do is find the horizontal asymptote or your end behavior. So look at the degree of the numerator. What is the degree of the numerator? 1. What's the degree of the denominator? 1. So again, we know that they're the same. So if the degree of the numerator is the same as the degree of the denominator, then how do we find the horizontal asymptote? We simply do what? Divide it. So it's going to be 3 over what? 4. So now let's take a look at number 3. What's the degree of the numerator? The degree of the numerator is a what? 3. What's the degree of the denominator? 1. So we know that 3 is greater than 1. So since the top is bigger than the bottom, what's the horizontal asymptote going to be? There isn't one. So now the question is, we've got to look at the end behavior. Is it going to be going towards infinity, or is it going to be going towards negative infinity? So again, we want to know the behavior as x is approaching negative infinity. Well, as you're approaching negative infinity, think about your x and y axis for a minute. As x is approaching negative infinity, you agree with me, we're on the negative side of the x-axis, correct? So we know that in this function that we're going to be plugging in negative x values. You agree with that? So it doesn't matter, just imagine if you can. If I plug in a negative number for x, no matter how large of an x number I plug in, the value of this numerator would be what? Positive or negative? Negative. You agree with that? Over. Again, I plug in a negative number for x. No matter how large I plug in, what's going to happen with the denominator? That's also going to be what? Negative. So a negative divided by a negative is going to be a what? Positive. So no matter how large of a number I plug, or how small of a number I plug in for x, no matter what happens, that numerator is going to be negative, that denominator is going to be negative. And I know a negative divided by a negative is a positive. So what that means is that the end behavior is going to be going towards positive infinity. So if there's no horizontal asymptote, and you're trying to find the limit as x goes to positive or negative infinity, then just imagine plugging in those numbers for x. If this was a positive infinity, I would be on the positive side of the x-axis, and I'd be looking at those positive numbers. All right? So now, properties of limits. So some rules that you're going to be following involving limits. If you have a number that's a constant and you want to find the limit is just simply that constant. So as you're approaching positive or negative infinity or a number, the limit of a constant is always a constant. So for example, if I ask you to find the limit as x approaches positive infinity of 3, the answer is just 3. The reason why is because we know that when you graph a function y equals 3, we know it's just a straight horizontal line. So you agree with me that's what the graph of y equals 3 looks like. So notice, no matter where I am on this graph, the y values are always going to be 3. So that's why the limit of any constant is just that constant. So what's the answer to 3a going to be? The limit as x approaches infinity of 5 is just going to be what? 5. The limit as x approaches 2 of 5 is just going to be 5. The limit as x approaches negative 100 is also going to be 5. So anytime you're asked to find the limit of a constant, it's just that number. When you're asked to find the limit of a sum, what you can do is you can find the limit as x approaches infinity of f of x, find the limit as x approaches infinity of g of x, and add those two limits together. So you can find the limit term by term and then add those limits together. That's your addition rule of limits. This also applies for subtraction. So if you're finding the limit as x approaches infinity of f of x minus g of x, you can find the limit first of f of x, find the limit of g of x, and then subtract. So that's your addition and subtraction rule of limits. Multiplication. If you want to find the limit of a product, you can find the limit of f of x, multiply it by the limit of g of x. So find the two limits individually and then multiply them together. You also have a quotient rule of limits. If you're asked to find the limit of a quotient, you can take the limit of the numerator and then divide it by the limit of the denominator. So find the limits individually and then divide them. If you're asked to find the limit that involves a radical, what you can do is you can just find the limit of whatever f of x is and then take the root of that particular number. Okay? So these are properties and limits that we can use. So let's take a look at 4a. So the limit as x approaches infinity of x squared minus 3 over 2x squared minus 5. So what we can do is you can find the limit using your subtraction rule. I can find the limit of x squared minus 3 over 2x squared minus the limit as x approaches infinity of 5. So you have a fraction. Limit as x goes to infinity, so what do I actually need to find with this fraction? I'm going to find the horizontal asymptote. What's the degree of the numerator here? The degree of the numerator is what? 2. Degree of the denominator is 2. So how do I find the horizontal asymptote? By simply make a what? A ratio, a fraction. So what's this fraction going to be? 1/2. Minus. Now the limit of a constant. What's the limit as x approaches infinity of 5? 5. So the 1/2 minus 5 is going to be negative 4.5. So you find the limit individually and then you subtract them. So any questions on that? So looking at B, you're trying to find the limit of a sum. Again, we can find the limit as x approaches negative infinity of x over x squared plus 1. Add it to the limit as x approaches negative infinity of 2x to the third over x squared plus x. Again, we're doing the limits as you go to infinity, so you want to find the horizontal asymptotes. So looking at this first one, the degree of the numerator is what? The degree of the numerator is a 1. Degree of the denominator is 2. So when the degree of the numerator is less than the denominator, what's the horizontal asymptote? 0. Plus. Now the limit as x goes to negative infinity. What's the degree of the numerator? The degree of the numerator is what? 3. The degree of the denominator is a 2. So when the top is bigger than the bottom, do you have a horizontal asymptote? No. So we know that this is going to be infinity or negative infinity. You can't take 0 and add it to infinity or negative infinity. Infinity and negative infinity are not a number. It's not a number. It's a behavior. So this is going to be a D and E. You don't say infinity or negative infinity plus 0. It's a D and E. All right, it doesn't matter if it's positive infinity. It doesn't matter if it's negative infinity. You can't take, that's not a number. Even though it's 0, you can't add it to 0. Yes, Peyton?
For these townhomes, are we gonna get points off if we don't write it, that addition layer?
No.
We do have room.
Yeah, that's fine. So now let's take a look at letter C. Again, even though this top part is factored, imagine if you were multiplying this out. What would the degree of this numerator be if you were to FOIL this and multiply it out? What would the degree of the numerator be? 2. What's the degree of the denominator? 2. So again, the degree of the numerator is the same as the degree of the denominator. So what is the horizontal asymptote going to be? 1/2. Because even if I multiplied this out, the leading coefficient would still be a 1. Now, you have a negative exponent here. So before we do the limits, let's get rid of this negative exponent. How do you get rid of the negative exponent? Move it to the denominator, exactly. And what's going to be on the top if I move this to the denominator? 1. So now, what's the degree of the numerator? The degree of the numerator is a what? It's a 0. What's the degree of the denominator? 4. If you were to multiply it all the way out, the highest degree would be what? 4. So again, the degree of the numerator is less than the degree of the denominator. So where's this horizontal asymptote going to be? 0. You guys go ahead and try the next 2 on your own. So did we come up with 5 for E and 2 for F? Okay. So any questions, guys, on how do we handle limits at infinity? Again, we actually did this back in Unit 8, where, again, when we were doing our rational functions, I had you start finding limits as you were going to positive and negative infinity. Again, it's either going to be horizontal asymptotes or positive or negative infinity. Again, now you got to incorporate those properties. Just remember, guys, going back to B, infinity is not a number. So, again, if one part is infinity, and even if you get a number on the other part, infinity or negative infinity rules, that is going to be a D and E. All right, so just be careful about that. Any questions on what we did for today? All right, then we are done. So you have the rest of the time, guys. You have 2 things